Hi guys, so this is the October 20th lesson. As you can see, you need to make sure that you have your composition books out, and then you are going to complete the exit ticket that the sub hopefully passed out to you by the end of this lesson. For your do now, what I would like you to do is to explain in your notebooks why the melting point of magnesium is higher than that of the melting point of sodium. You're going to complete this question, and then once you have answered the question in your notebooks, you are going to come back after you have answered and then revise your answer based off of the information that I'm going to tell you. So go ahead and pause the video, write your answer, and then come back. All right, so thinking about this logistically, magnesium, the magnesium metal, when we're talking about metallic bonds, donates 2 electrons to its electron C to become magnesium 2 plus. Sodium only donates 1 electron to the C. Plus, from what we learned from last unit or the units prior, magnesium is going to have a very much smaller ionic radius than that of sodium. So the more electrons you have in the lovely delocalized sea of electrons, plus the size of the ionic radius being smaller, magnesium is going to have a much harder melting point to melt that metal rather than sodium. This is why sodium is a lot softer than that of magnesium as well, and it contributes to the melting point of sodium being lower than that of the melting point of magnesium. So this is reviewing those periodic trends that we had 2 units ago. Today we are only going to focus on carbon. So carbon has a very unique, interesting structure rather than majority of the other non-metal structures that we have talked about. So some covalent structures are crystalline in nature, like an ionic lattice. However, they are linked together with covalent bonds. The crystal is a single molecule with a regular repeating pattern of covalent bonds. So this is a massive structure we're talking about. We're not talking about little intricate structures. We're talking about a giant covalent structure for this. It is referred to as the giant molecular structure, and allotropes are different forms of that element, but they basically have the same physical states, which all of these are solids. They just have different properties to compare between rather than the normal properties that you're used to. And they are bonded differently within their structures as well. And then carbon has 4 allotropes, which will be shown in a video that I am going to show you. However, to review some things, let's talk about some structures. Okay, so first thing we have is a lovely giant ionic structure, which has a crystalline structure of itself. The example of this is sodium chloride, and they are electrostatically attracted to each other, and that is what is holding the bond together. There are no IMFs in this lovely structure because, again, we're talking about ionic bonded things. They are only having an electrostatic attractions between each other. Now let's go to giant covalent structures, like, for example, diamond. Diamond is a crystalline structure that is held together by bonds, and they are very strong covalent bonds since we're talking about carbon being bonded to carbon and making this giant covalent structure as well. Because of this, also diamond has no IMS because it kind of mimics what we know about a giant ionic structure as well as the giant covalent structure. And we're only talking about carbon being bonded to itself. And it's really thankful that diamond doesn't have any intermolecular forces because it would be bad if we were to react it with water, acetone, etc. Simple covalent structures like water do essentially have a non-crystalline like structure. They are mostly held together by their weak forces that they have, whether it be van der Waal, Dunlin dispersion, dipole-dipole, and hydrogen bonding, which we'll get to later in this course. So you'll have to understand those a little bit later. But essentially, it's very rare for them to be crystalline. They're mostly liquids and gases at this stage. And those do have IMFs because they are being held together and interacting with the other molecules that are there. The last one is the giant metallic structures, which, as you know, are essentially crystalline structures where you have that lovely ionic radius of the metal surrounded by a sea of delocalized electrons. So we're just simply reviewing the structures of each thing, and I'm just adding an additional one of the giant covalent structures. So let's review IMFs. So giant ionic doesn't have IMFs, giant covalent doesn't have IMFs, and neither does metallic. Only simple covalent molecules do have IMFs. These simple covalent molecules can be massive and they can be crystalline in nature, but majority of the time they are not. Okay, so let's talk about the first allotrope of carbon, which is diamond. Diamond is arranged in the structure to the right as the following. It is bonded covalently, and it has a very high melting point, which is Tm, and the strength is very strong. Now, diamond does not conduct electricity, but it is held together by extremely large bonds, and it's extremely hard to break. So, diamond is all made in nature, and it's also made in laboratory settings, and it contains no charged particles or no electron ions. So, it's a really good thing that diamond does not have any current that can be carried out. So it's mostly used in jewelries or blades for hard cutting objects, because we know that we have a diamond crusted or diamond infused tip for drills and stuff like that, because it's really hard to break. The other one is graphite, which a lot of you are basically using right now for your pencils. It is another giant covalent structure, has a very high melting point, but it is way softer than diamond. This is because it is arranged in sheets and does have very weak van der Waal intermolecular forces between its molecules. Now, in this, the carbon's only bonded 3 times. If you look here, this one carbon here is bonded only 3 times, allowing 1 electron to be delocalized in the structure, allowing electric current to run through. So that's why there are some graphite batteries and wires that we use today in this world. It's because graphite is allowed to have the electron be transferred from one place to the other with those delocalized electrons. And it is used as electrodes and as you are writing right now with the pencil. So it is good electrical conductivity, and it is made by hexagonal planes. And then the delocalized electrons allow these sheets to be interacted with each other through the delocalized electrons transferring from carbon to carbon. Now we're going to review ice. So ice is a little different. Ice is held together by the hydrogen bonding of the water molecules that you have. Now it is covalent. It's held together by hydrogen bond intermolecular forces. It is simply molecular, but it does mimic what we know as the lattice structure. It has a very low melting point, and it has very weak IMS, but they are held together by these forces in order for them not to break. There are no charged particles in water, hence why water cannot conduct electricity. And they're used to keep your drinks cold and also preserve food. Okay, iodine, another simple covalent compound, usually held together by van der Waal forces, has a very low melting point and very weak IMS, as we know because we were talking about van der Waal, which we will get to what van der Waal means later in this course. And it does not conduct electricity whatsoever, but it is a diatomic molecule that contains no charge, so therefore nothing can be passed through it. I'm just showing you essentially, because iodine is one of those crystalline structures, it is held by van der Waal forces, which is very weak, hence why it's easily able to vaporize at certain temperatures, and it's mostly used as a disinfectant to reduce a thyroid hormone. Then we have magnesium, your lovely metallic bonding, which is basically intertwined by a metallic structure. Very high melting point, allowed for electricity to go through due to the delocalized electrons in the sea. But these delocalized electrons allow these ionic radii of the magnesium metal, or the ionic ionic ions that you have being held together in order to make sure that the metal is, held together by these lovely ions that we have being made from the delocalized electrons. And the delocalized electrons allow electricity to go through. And these are mostly used in fuses. Last but not least, you have what is known as sodium chloride, which is an ionic structure, giant ionic structure held together by electrostatic forces. They have very strong electrostatic attractions. They are mostly really hard to melt, but when they are molten, they allow electricity to run through them because they are in their constituent ions at that point, whether they are molten or in a solution, and charge can move from the positive cation to the negative anion very well. And again, we love salt. It's used to preserve meat, and it's also used for seasoning food. Now, here are all essentially giant covalent structures that you need to know. Silicon dioxide is essentially your windows, your glass that you have. These are held together by very strong covalent forces that essentially, when they are combined together, make almost like a lattice-like structure, which is very hard to break, but it's not as strong as diamond, because if you drop glass, glass breaks. Now, here are the other allotropes of carbon. So there's only 4 that you need to know. You need to know graphite, graphene, diamond, and fluorine, which is also known as a buckyball. What I would like you to do currently, right now, after I go over the next slide, is to watch the allotropes of carbon video and take notes on that. That is from the organic chemistry tutor, and it will be very interesting for you to figure out how these are used. Now, let's review. Giant covalent, there are no IMFs, have very high melting points, and are usually can be solid, liquid, or aqueous, but majority of the time they are solid. Giant ionic lattice structures are bonded by electrostatic attractions, have very high melting points, and are usually solids, but conduct in both liquids and aqueous solutions. This is how they conduct. So giant covalent does not conduct with any of these, but if we go back, graphite does conduct electricity, which you will also find out one other also conducts electricity as well. Symbomolecular is essentially like those tiny little water or iodines. They do not conduct electricity. It depends on the molecule if they have IMFs and they have low melting points. And the metallic, obviously metallics have no IMFs, have very high melting points, and then conduct electricity as a solid or a liquid, and normally times never are aqueous, because if they're going to become aqueous, they're going to become ionic salts. So what I would like you to do, before you get to your lovely exit ticket, go on to the Schoology where you found this lovely video, watch the allotropes of carbon video, and then once you have that completed and done, what I would like you to do is then answer your exit ticket and turn it in the bin before you leave. I hope you guys are having an amazing day. You guys have a great rest of your evening. And then make sure that for these reasons that you're also going to page 135 to 137 to answer those questions for homework, because I'm going to ask you about those tomorrow. You guys have a great rest of your day, and thank you for watching my video.